I see there are quite a few people who are actually just ALMA, well, people using ALMA as principal investigators or as data miners. So hopefully this talk is useful for you. This is just talking about how to work with the WebLog, and it'll also briefly mention some of the other material from the archive as well. You will have seen these instructions already, potentially, but we put this demonstration data set online, but you can bring your own weblogs for your own projects. There are odd security features in a lot of web browsers which make it difficult to open the weblogs properly. So there are a couple of options to get around this, and we recommended that people use Firefox because it's relatively easy to circumvent some of the excess security features. Just to show, so I'm actually going to bring in Firefox here and the instructions here as well, which I'll try to resize so that you can see them above the Firefox window. If you go into Firefox and type about :config, and then you'll get asked changing advanced configuration preferences, just accept the risk and continue. And then in the next page, search for privacy.file_unique_origin, and then set this to false. You've seen that I've already set this way. There's this button here that changes it between false and true in this particular version of Firefox. After you do this, after this is set to false, restart Firefox for it to take effect. So I'll just continue on with the discussion of getting to the weblog. So when you download the ALMA archive data, you'll get data sorted into a directory structure similar to this, where you'll have a directory with the project ID, which begins with the year when the proposal was submitted, so something like 2016 or 2018, a science goal or potentially multiple science goal directories under that, depending on the program, where they'll end in a couple of hexadecimal numbers. Then there will be potentially one or more multiple groups within each of those science goal directories with more hexadecimal numbers, then one or more member UID directories with more hexadecimal numbers. And then within each member UID directory, there are generally these types of directories. The stuff we're going to be talking about today is in the QA directory. So the QA directory for pipeline process data will contain these files with the following suffixes. There will be a file which ends in weblog.tgz, which is the one we're going to be talking about today. There are also the QA0 report, QA2 report files as well. These are the files that you get for pipeline process data. For manually calibrated data, you will get a series of PNG files with diagnostic plots and a PDF, and I'm not covering those in this presentation. QA, if you aren't aware already, stands for quality assurance, and there are 4 phases of quality assurance in ALMA, which are labeled QA0 to QA3. QA0 are some simple quality checks which are performed at the observatory as soon as the data are acquired. QA1 is something that most people never hear about. It's long-term monitoring of the performance of the observatory, and there isn't a specific QA1 report written for any specific project. QA2 is what a lot of people in the EU ARC put the most effort into, and that is a complete quality assessment of the data after the data are completely calibrated and imaged. And the WebLog is very useful for in the quality assessment for pipeline process data. And then there's also this final stage, QA3, which is a reassessment of the data after they are delivered to users. That is triggered when the users, it could be the original PI, I think it could be somebody else, or it could be just an ALMA scientist as well, discover some previously unidentified problem where the data need to be reprocessed to be in the scientifically usable form. I'm not going to talk about the QA0 and QA2 PDFs in much detail, but just to mention them briefly, the QA0 PDF provides some very summary comments from the astronomer who acquired the data. You can see the final QA0 comments here, and some simple diagnostic plots, and this is one of them showing system temperature, which is background emission. I'll talk about that later, as a function of antenna. But there are many more plots besides this one. The QA2 HTML and PDF files, which are just alternate formats, the same information, provide some comments on the data processing and summary information about the observations, which you can see here. But then the last few pages after this page includes standard instructions sent to all users on how data can be unpacked and recalibrated. The WebLog contains most of the useful diagnostic information from the QA2 process, and this is produced by the ALMA pipeline as data are being calibrated and imaged. And again, just to emphasize, the WebLog is something created by pipeline calibration. If you look at data from very early cycles, those data were mostly manually calibrated, and so you won't have access to any WebLog information, but definitely from cycle 5 and maybe even part of cycle 4 onwards, you will have primarily WebLogs for most of the stuff in the ALMA archive. The calibration is the part of the pipeline that will calibrate these 4 things in the visibility data. So you have phase versus frequency, amplitude versus frequency, phase versus time, and amplitude versus time. The amplitudes, of course, are related to the flux of the final objects. The phases are related to positions of the objects in the images. The imaging pipeline will also produce image cubes. These are not necessarily science-ready image cubes, but, well, they aren't science-ready in the sense that they're going to be suitable to all people's scientific needs. They can be used for science, but it's more than likely that people may need to reprocess their data to create image cubes that meet their specific needs. That's an entirely different topic for an entirely different training video. But there are image cubes that are available. There are continuum flux images, which are available for each spectral window. And then there's an aggregate continuum image for all spectral windows. Or that should actually be called aggregate flux, because that may include spectral lines in creating the image as well. The WebLog is typically distributed as a set of HTML files in a TGZ file that needs to be uncompressed before the files can be viewed. And the overview page is within the resulting directory at index.html. So to pull this Firefox window back, so assuming that you've unpacked the .tgz file. You want to go into Firefox, again, after reopening it, after setting this security option. And then in this case, this is the WebLog example. And then when you unpack the WebLog example, you get this directory called pipeline with a very long set of numbers after it. Inside that pipeline directory is another directory called HTML. And then if you go inside that directory, you'll see you get a large list of folders as well as a list of HTML pages. Now, I normally work with weblogs in Linux, but I'm running this demo on a Windows computer. In Linux, when you unpack the data, you'll get an index.html file, which is actually a shortcut to T1-1, I believe. Unpacking the file on Windows, it did not create this index.html file, so I just created the link anyway. So if you click on that, or if you click on T1-1, going to create more space, but you should get to this overview page. And this overview page provides, okay, the directory naming is when the pipeline process was activated to run at the ALMA regional centers. So that explains where the names come from. So if you look at this overview page, which is also the home tab here, you can see the project name, principal investigator, the OUS number, information about the pipelines. We can see that this was processed in CASA 5.4.0, and there's the pipeline start, and this took 8 hours and 22 minutes to execute. At the bottom of the page, you see that there's this table with 2 measurement sets listed in it. One of them has just .ms at the other one, and the other one has target.ms. The difference between these two is that in the first one, this contains all of the data, including all of the Calibrator data. The other one just includes the target, the science target data. It's more interesting to look at the first one, though. So click on that link, and this will take you to this page, which gives you an overview of this individual execution block. Also worth indicating is that this particular example has one execution block. If you have a scheduling block with multiple execution blocks, each one will have its own entry here. Now, there's this page with a lot of information in it. I'll just walk through some of this already. For those of you who are used to manually calibrating ALMA data through CASA, you can click on this link, which gives you this list obs output, which gives you text information with an overview about the observations, including like the sequence of observations, the field IDs, the spectral windows. This includes a lot of the spectral windows which are not used in the science calibration itself, but are used in the a priori calibration. And then also scrolling down here, we have the antenna list as well. That's actually a useful reference in general. Sometimes I end up spending a lot of time looking up stuff in that. You may want to open that in a separate tab. The intent versus time and field versus time pages are kind of just to keep up the tabs here with what I'm talking about. So the intent versus time shows a sequence of observations as well as the purpose of those observations. So we have the first observations are a combination of a wire vapor radiometer observation and pointing observation. Then there's an atmosphere variation. This is where the system temperature is measured, which I'll discuss later. And then there are observations of a calibration source, which is used for amplitude and bandpass calibration, but there are also water vapor radiometer observations. And then this sort of continues. Eventually, we'll get to the phase calibration observations, and then the science target, and then phase calibration observations after that. This is a very short observation. As you can see, it just sort of does one scan on the science target. So it's very short. Was part of the reason why we chose this demo. The field versus time plot, similar to this, except for now the y-axis includes the field ID. And so this just sort of shows that field 0 is the field that is used for the amplitude and bandpass calibration. Field 2 corresponds to the science target, and field 1 corresponds to the phase calibrator, which is in the cyan here. Next is the, so there are several other tabs, which I'm not going to go into in detail here. The antenna setup page is kind of nice because it shows the location of the antennas and also the resulting UV coverage as well. And these are just nice references for a couple of different reasons. First of all, you can do some simple math to identify what the angular scale should be of the final images, as well as the maximum recoverable scale if you're worried about large scale structure, just based on UV coverage. There'll be lots of pages which will show that stuff later. The antenna positions also just show you where the antennas are. And now this is a relatively compact configuration, but if you have a more extended configuration, you may have antennas which are further away from the center, and those antennas that are further away from the center may tend to be more noisy in the data. So it's worthwhile looking at these plots to be able to identify them. This is just an alternate layout plot where it shows the antenna layout in reference to the reference antenna, DA54. And so you can see the furthest antennas are less than 300 meters away in this particular observation. This is kind of a funky logarithmic scaling. To go back, so if we go to sky setup next, this just shows, again, it shows UV coverage on the right, but it also shows elevation versus azimuth and elevation versus time, which just give a sense of where the various fields are in the observation. So in this particular case, because I just kind of recognize this at this point, this is the science target observations at this point, and usually they're long observations which are near some other field which is measured periodically, which is this. This is the phase observation. So what happened during these observations was that the phase source was observed first, then the science target was observed, and then the phase observations were observed after that. And then before all of that were the bandpass and amplitude calibration observations, which are over here. So you usually have like one field which is somewhere very far away in terms of elevation and azimuth, but the phase calibration observation should be kind of close to the science target. If they're kind of separated by a large distance, then you kind of have to worry about the calibration in the data. This is just an alternative look at the data with elevation versus time. So it just shows that these fields are separated by about 5 degrees in elevation, which is just sort of nice. And then you can see that, again, this, which is the bandpass calibration, is very far away. If you have more than one science field, for example, you may have more than one color in this plot. So next, going to the weather and Pwv plots. These just show what the weather conditions were like during the observations. a couple of different things to look at. You want to look at the humidity. This actually shows, I hadn't noticed this before, but this shows the relative humidity is kind of like close to 100% in one of the weather stations. But then the other thing that matters too is the PWV in terms of this. You just want to look at some of the numbers in general, just make sure there aren't any wild fluctuations otherwise. So the temperature stays constant. The wind speed's kind of low, so don't worry about the wind speed varying that much in this particular plot. But if you had wind speeds around 30 meters per second, for example, or if the wind speed suddenly jumps at 30 meters per second, then you'd want to be concerned. Similarly, when the winds are low, don't worry about the wind's direction jumping around that much. This is the PWV plot. And, I think that's kind of high. You can see that the precipitable water vapor does vary relatively smoothly over time. You can't, where it's hard to see some of the data points on the edges here, but you can see this varies relatively smoothly. You don't have a sudden jump where the conditions suddenly deteriorate during the observations, or conversely, you don't have like a sudden drop where the conditions suddenly improve, which would actually be kind of beneficial. Although it would still lead to potential weird effects in the data later. And that's most of the stuff here. There are other tabs which didn't click on, but those seem to be the most important ones. Going to the by topic page, so you get several different things here. First, at the top, you get this list of warnings and errors, which we'll check out later. And I'll explain what these warnings mean, but it's good when you see these warnings to actually go check the individual modules. This next row, we actually see scores, and it generally looks like if we have scores which are below 0.66, those are things which are something of a concern. I would say it's still worthwhile. It's just looking at things which aren't a score of 1. This is something where we can look at, but maybe don't need to be too concerned about. But this one here, the beam is not in range, is something that we should take a look at, and we'll discuss a little bit more later. And then at the bottom of this page, we have flagging summaries. We'll have one set of tables for each measurement set, or in the scheduling block, but in this case, we only have one measuring set, so we only have one set of tables here. And note that you have to make the window large enough so that you can see this scroll bar be able to go all the way to the right. If you make the window too small, you won't see the edge of the window. And this tells you how much the antennas are flagged. It's generally, first of all, antennas which are flagged 100% are not usable. So there's some problem with DA57 in the observations. We have separate tables for each of the sources, I forgot to mention, by the way. So, and they aren't put in a particularly good order in this particular case. So this was the phase calibrator source, then the science target, and then the third table here is for the bandpass and amplitude calibrator. You can see DA57's flagged in all of these, so something went wrong with DA57. You can see DV06 gets flagged in the amplitude and bandpass observations, so something went wrong with DV06 in those observations. We should check it out later. Generally, you want these numbers to be below 20%. If you see numbers here which are higher than 20%, you just want to go check that. Also, I should mention that the numbers here in this table, Should have discussed this. So yeah, this is antenna along the top here and then spectral window along the bottom. And this observation is a little bit different from many ALMA observations, and that has 8 spectral windows, or 10, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. It has multiple spectral windows. It presumably the ALMA pipeline would have taken care of like the things which are flagged already. If you see an entire field where all of the data in that field are flagged by more than 20%, there could be reasons for that, such as a significant portion of the data was a priori used for a priori calibration, but wasn't actually needed for the science calibration, and so got flagged part way through the calibration. You could also have a lot of flagging because of shadowing in the ACA, for example, but that's not necessarily something to worry about either. And now to the by task page. So if we click on the by task tab, we see a summary list of all of the calibration steps which are applied to the data, as well as the scores here and various other messages, and even exclamation marks and question marks, which indicate that there were warnings or things to check with the individual tasks within the pipeline. And here we see the this task number 22. We'll look at that later. But you see most of these got a score of 1. There aren't that many warnings. And some of these warnings are really kind of minor things, as I'll discuss later. Going through these tasks one by one. So if you click on one of these tasks, we'll start with number 1, which goes to the import data page. So this just gives you detailed information on, or detailed diagnostic information from the task. In this particular case, this just imports data from the pipeline, but the one notable thing here is that it lists the model flux densities for the calibration source, or the calibration sources. So field 0 is going to be used for the flux calibration, and so these are the fluxes, or the flux densities, which are going to be assigned to each of the spectral windows. Field 1 is the phase calibrator, and these fluxes came from, actually both these sets of fluxes came from the catalog, and these are kind of used more for reference, as I'll show later, but these are the ones which are going to be used to rescale the data. So if you think you have flux calibration problems, you should check these numbers against data from the ALMA calibration source catalog. And if you find problems, contact your local ARC. Next step we're going to cover is HIFA flag data, which performs a series of a priori flagging steps, and which are summarized in this table here. Ideally, you want the numbers to be less than 20%, or roughly 20%. If you go slightly over 20%, that's not an issue. If you're flagging 50% of the data, you may want to get help. And there's also these plots which just show summary flagging information versus time in kind of this colorful way. So this shows each of the antennas on the y-axis versus time on the x-axis. And then there are these little colored bars. There's one colored bar for each spectral window, which just, or sometimes for each spectral window. Sometimes it's done that way. Sometimes, I guess it's not done that way here, right? Okay, so anyway, there are these colored bars which just indicate why data were flagged for each antenna. And so they're kind of mundane things like basically saying the antennas are not ready to perform observations. Next module we're going to go to number 4. So there's more flagging, which is done here. Again, the percentages should be below 20%. If you click, just to show that, because it might have been quick, if you click on display here in the table at the top, you do get this nice graphical display of the spectral windows, which just shows where data have been flagged. Well, it says cannot calculate. You see all of these pink bands in the data that there was this one bad antenna, and that's probably showing up as this pink band here. This is baseline, by the way, on the y-axis and not antenna. So it's not listing stuff by antenna, but by baseline. And so there are like lots and lots of baselines here. So 47 times 40, or excuse me, 48 times 47 divided by 2. So you have like one column in this image for each baseline. And so there are a lot which are where it could not calculate stuff that may be related to DA57. You can check each of these potentially if you want. Oh, I went back one too many pages. So next, T-sys-cal. Here there are Apiary amplitude calibrations derived based on the system temperature of the data. Just to explain what the system temperature is, so these are, for people who don't know details, these are measurements of background emission from the sky and from the telescope and the instrument, which are used to perform an amplitude correction on data, or an a priori amplitude correction on the data. So if we click on each of these plots, these shows the system temperatures that are derived initially for the data. You see little bars in this plot showing where each of the spectral windows are located in this frequency range. So the system temperature, I believe, is measured over this entire frequency range, and then there are corrections derived and applied to each of the individual spectral windows based on this measurement over the broader range. And you can see that there's some noise and some edge channels. That's okay. Those generally get flagged. You can see there are some wiggles and some variations in the data, but there aren't any severe outliers. So there isn't a line which is above 200 here, which would indicate an antenna where there are problems with the system temperature measurements, and potentially other problems as well. You also see the atmospheric transmission plotted as magenta line here. In this case, the atmospheric transmission is relatively flat. In this plot, we can see that there are issues in the system temperature in a very small frequency range here, which is okay because it doesn't cover any spectral window, but these should be flagged. We'll see that they're actually flagged by the pipeline. Here we see a dip in atmospheric transmission, and this corresponds to an increase in system temperature. This is okay. This is the way it's supposed to look. And if the pipeline works correctly, this should be, this variation in transmission should be removed from the data. Not just by this step, though. And then finally, here's the fourth plot as well. Now, in the next step, so we get a couple of warnings here. I'll come back to the warnings in a second, but this shows the same plots now, but removing the outline data. So this looks the same as before, except for now we've removed those edge channels. If we go to the next plot, you may recall that there were like a couple of channels where the system temperature spontaneously peaked. Those have now been flagged. And then we have this. Very importantly, the spectral feature in the data have not been flagged. That needs to be left in to properly calibrate the data. And then window 4. To go back to those warnings, so we have a warning about flagging edge channels, which is okay because it's we expected the edge channels to be flagged. And then there's a warning about flagging birdies. Birdies tend to be channels which are abnormally high. So it's those channels which peaked when we looked at the plots from the previous task. There are also some notes on the various flagging steps here. So the types of flagging which have been done, such as edge channels, birdies, and stuff like that. This next step performs an a priori calibration step based on these WVR measurements. The WVR, which you've heard me mention a couple times already, stands for water vapor radiometers. And these measure the amount of water vapor in the atmosphere along the line of sight and can be used to correct for phase effects related to those measurements. So the calibration is derived, I believe, just derived in this. It's either, it may be, actually, it looks like it's applied in this step too. Sometimes things are applied, are just derived in some of these steps, and sometimes they're derived and applied. The first plot that we get, it just shows where in graphical form, first of all, what the data look like before and after. The flagging in terms of the phase RMS. Well, okay, yes. This I think is this supposed to be? This looks like it's supposed to be with. Right. Okay. I don't quite know what the label is for the grays here, but this is a ratio of what the RMS is like before and after the application of this correction here. You can see some magenta lines here. These are places where calculations could not be applied. And then there's this orange line, which I think corresponds to DA57, which does correspond to DA57, where there was a problem with the data. The magenta lines are okay. There are occasionally antennas where we'll see this in, just to scroll down to this table at the bottom, you can see that there are a couple of antennas where there's a check mark in this column called interpolated correction. That's okay. Just as long as it doesn't happen too many times. It can happen for a couple antennas. To show some of the other diagnostic plots here, which are kind of useful. So we have plots of the phase. Yes, so we have plots of the phase before the correction, which are shown in gray here, and then after the correction, which are shown in the red and the green here. I don't quite understand these two outliers, which are a little bit of a concern, but then you see, what you should see for most of these data is that these large wiggles in the median phase should decrease after you apply the correction. And so in other words, the red wiggles should be much smaller than the gray wiggles in this particular case. And this is taken from 3 specific scans, 3, 6, and 9. So, oh, those are the Calibrator sources. Yeah. And that's also for one spectral window, just to point out. We also have this diagnostic plot, which is kind of nice too. So this shows on the x-axis the distance to the reference antenna. So this is effectively baseline length. And then on the y-axis in the top plot, we have the phase RMS without and with the water vapor radiometer. correction, which has, okay, in this case, it should be a number greater than 1 because it's without should be worse than with. And then this plot here, which I find more useful, is just a plot of before the phase RMS before and after, with the before in gray and the after in red. And you can see the numbers after are much smaller. You can also see that the RMS noise in the phases increases with baseline as expected. If you had the data point, which is like over here somewhere in this plot, where it's a short baseline but a very high deviation from median phase, that would be something of a concern, but we don't actually see anything that bad there. Next thing is the set models. This again just shows the flux densities which came from the catalog, but it also shows these nice plots here, which are just model plots for the data. We're working with a point source measured with a telescope with relatively short, or an array with a relatively short baselines. So we would expect these model amplitudes versus UV distance in these plots to look like straight lines, which we more or less see. If you've looked at these plots for planets, by the way, these would look like sinc squared functions, but I don't think any data with planets as flux calibrators have been calibrated with pipeline calibration, but you can create similar plots like this for early ALMA observations with planets. But most of the stuff that you should see from the pipeline, these should be relatively flat lines. Next is bandpass flag. There's a warning here that there were some additional flagging that was applied by this particular module or a particular task. That's okay. So this task derives the bandpass solution. This is now after all of the a priori calibration steps. There's flagging data summary here, but then if we keep on scrolling down, we get to plots, and these plots are very useful. Or at least they could be more useful in some of these cases. So this is a plot of bandpass versus frequency. So these are the bandpass calibration. Unfortunately, this particular example measurement set has very small, very narrow spectral windows, so it's we don't really see the bandpass calibration that well, except for this one spectral window, which is very broad. So a more typical ALMA data set with 4 relatively broad spectral windows will have 4 bandpass plots like this in this particular plot. All of these individual ones are a little bit too narrow to read in this particular plot. But we can see that this is a relatively smooth function. It doesn't need to be flat. It does need to be smooth. If you see really sharp spikes or something in this solution, then something has gone wrong in the observations. And this is, should check. Okay, so this is DA54, which is reference antenna. This is DA41, which is just the first antenna in the list. So these are 2 different antennas and showing the bandpass solutions for 2 different antennas. We also have phase versus frequency, which is more or less similar. It's okay to see some wiggles in the phase versus frequency. Note that they don't differ that much from 0, but this is okay. We also have plots of amplitude versus time. So this is the calibrated data before flagging. This is kind of a common feature to see these data points which fall below the majority of the data points here, but we can see most of the data points actually fall on a relatively straight line. You can click through each of these. This is a plot per spectral window. Yeah, one's, so that's corrected. Okay, calibrated data before flagging. So these are corrected plots, and you can see one for each spectral window here. And then calibrated data after flagging. There isn't that much difference, but you can look through each plot. Yeah, you can see this looks a little bad, but it actually gets corrected by the pipeline. And then we also have amplitudes versus UV distance, which is just nice to look at. So again, this is plotted for, well, this is bandpass calibration. So this should be for the bandpass calibrations, well, based on the bandpass calibration, it should be flat. So next is the G-flux scale flag, where here it tells us that it flags some additional data. That's fine. Outliers from the bandpass flagging should have been flagged before this step. And so this will produces more diagnostic plots. This is a phase. Yeah, no, this is amplitude versus the amplitude versus time for the phase calibrator. And you want these to be relatively flat versus time. There are lots of these plots. And then we have amplitude versus UV distance. Okay, I almost skipped one there. So now we have the flux scaling step, and now we see another one of these tables with flux densities, but now this is for the phase calibration stuff, and this is comparing the flux density which comes out of the catalog, which is shown in the bottom here, versus the flux density that's derived for the phase calibrator when applying the calibration from the amplitude calibrator, which is shown at the top here. These numbers in an ideal case should come out to be close to 1, which is actually the case for most of these. That's actually kind of unusual because usually the typical situation with the phase calibrator sources is that they're very rarely observed, but they tend to be very variable sources. So it could be expected that the source is observed once a year, maybe. And not because it's scheduled once a year, it just gets observed once a year by chance, because a certain program or another program just happened to require the same phase calibrator. It does not get observed in that 1 year period, but because it's something like a high redshift quasar, it varies in flux density quite a bit in that time period. So very often when you look at this page, you will find that the observed flux density doesn't match the catalog flux density, and that would be fine. It's almost kind of unusual to get the observed flux density for the phase calibrator to match the catalog flux density. Now that's for the phase calibrator. For the amplitude calibrator, and that's not shown here, but it should be the case that when you look at the flux densities for the phase calibrator after the calibration have, or excuse me, when you look at the flux densities for the amplitude calibrator after the amplitude calibration has been applied, that should equal what's in the catalog. You should really go check the images for that type of thing. I don't know that there's a specific table that shows that type of thing. But that should be the case. And if that's not the case, then there could be issues with the flux calibration. You also do see some of these diagnostic plots here as well. This just shows the flux calibration, which comes from the calibrator sort, or the calibration catalog, versus the measurements which come out of this particular measurement set. And then you see various model plots as well. Sorry, I realize I'm running a little bit slowly, but okay, so this is where a lot of the gain calibration is derived. These are corrections in phase and amplitude versus time. And this produces a huge number of plots. First, we have phase, or the gain in the phase versus time. We see different gains in these three measurements, but recall that the first gain measurements would be for the bandpass and amplitude calibrator. That's usually a brighter source, so we expect the phase and amplitudes to show less scatter here, whereas the phase could be fainter and therefore show more scatter per individual antenna. But the numbers are kind of close to flat. Next, we see phase RMS versus distance to antenna. Ideally, this should look like a straight line going upwards, but we see there are a couple antennas up here, but that's kind of, it's okay in this particular case. We don't, actually, we can't go off more than 180 degrees, I don't think. Next, we have amplitudes versus time. This is for, oh, okay, yeah, so this is for the, or let's see, oh, this is the gain versus time. We see that there's one antenna where the gain is a little bit different from everything else. And if I were manually calibrating this data, I would be paranoid and flag this, but it works just fine as run through the pipeline calibration. But you can see that one outlier antenna in some of these spectral windows. If something deviated by much more severely, it would be something of a concern. Now we have phase versus time now. This is showing all antennas and correlations. Okay, so yeah, okay, I'd have to go look. Sorry, I don't know all the details of every single plot here. The top plots show more average data. This is showing individual measurements. We can see in some of these plots there are, oh, this is actually phase wrap. So this is actually okay. There are a couple data points at the bottom because this is like data points which went over the top. Phase offsets versus time, that's kind of close to 0. And amplitude versus time. We see, yeah, we have some data points which fall a little bit low from one antenna, and then like everything else is kind of flat. If you want to identify the antenna, what you can do is click on any of these things that say Spectral Window. Shouldn't have done that. Don't right click on them. But you can get plots for each individual antenna here if you want to inspect the numbers for the individual antenna. So if we want to find that antenna with the really low flux densities, or excuse me, the really low gains in this particular case, we would go look here. And you can click on the individual plots to expand them. Okay, I think I accidentally skipped a couple of things trying to click through, right, apply cal. So this was derivation of the gain calibration, and then this is the application of those phase and amplitude corrections. And we're going to get many, many more plots. So this is after the calibration is applied, and these data should look much nicer now. This is for the amplitude calibrator to begin with, and this is showing the atmospheric transmission at the top. So we should get numbers which are more or less the same and close to what's been listed in some of those tables, which list the flux calibration for these sources. But we see that these data look flat. We don't see any abnormal spectral features. We can click through each window. What may be kind of interesting is something like this one. So this is for Spectral Window 43. The magenta line again shows the atmospheric transmission. You can see where the atmospheric transmission decreases, the scatter and the data increase, but the data are still close to an average value across this spectral window. And that extra scatter is fine. It would be potentially my personal preference to experiment with flagging those data, but you can leave those data in. And we also see that here, this may be for, so we have a set of plots for the amplitude calibrator, and then we have a set of plots for, and then we have a set of plots for the bandpass calibrator, but that's the same as the amplitude calibrator. And then we have a set of plots for the phase calibrator. Then we have calibrated phases versus frequency. These should be close to 0 for the calibration sources, and they are. Again, it's like as you approach the edge of spectral window. So we remember spectral window 43, the atmospheric transmission decreases towards the high frequency end here, and we see a little bit more scatter in the phases, but that's okay. Also, we see this is relatively flat, but I think this is the one really broad spectral window. So this is, it makes sense that this is much flatter than the others. Let's see, I'm sort of rumbling through. Okay, so these are the phases for the phase calibrator. It's a fainter source, so you see more scatter. Again, this one spectral window, it's there's less scatter than any of the other spectral windows. And we get calibrated amplitudes versus UV distance for first the amplitude calibrator. This should be a relatively flat line at this point because it's a point source. Yeah, we do get like the data dropping off, but that happens. Phase, so we have the bandpass calibrator, which is the same as the amplitude calibrator, and then we have the phase calibrator, and then we have calibrated amplitudes versus time, which are kind of an interesting plot to look at. So you can see that the amplitudes look close to 0 for the science target, which is the orange data here. That's fine. It's probably not at 0. It's just it looks that way in the visibility data. But this just shows the bandpass amplitude calibrator, phase calibrator, target, and then phase calibrator. And we get one of these plots for each spectral window. Something interesting happens there. This is probably a spectral line in the science target, or a real spectral line in the science target. But because we're looking at the data in a funny way here, it's hard to tell what's going on. We get phases versus time. These should be close to 0. Let's see, the corrected amplitude versus the model. We see that there are some issues with antenna 30. If we go back to that list.ops file, we could look up what, and actually we have the list.ops file here. So if we look up antenna 30, that corresponds to DV09. So for whatever reason, this shows a little bit more scattered and everything else. We may want to experiment with flagging that antenna to see if that improves things, but otherwise it may be okay. We may also want to check to see if that just happens to be an antenna on a long baseline, in which case then it may be expected to show more scattered than the other antennas. These are plots for the phase calibrator. Corrected amplitudes versus model versus UV distance. This should be flat, or it should get worse as you go to longer baselines. That's okay. And then science target, calibrated amplitude versus frequency. And this could be a place where you can actually look at, so this is actually the science target now. And these are places where you can actually look to see if you can actually see spectral line data in the visibility data before making images. And we see that there is one strong spectral line here. Nothing very obvious in the other data. And then science target, calibrated amplitudes versus UV distance. If this is actually a place before making images where you can see if there's structure present, and you can actually see there's something other than a flat line here, which indicates that, yeah, there is some sort of structure which was seen here. This was the spectral window with the spectral line, so that spectral line has some sort of spatial extent. And then you can also, this was that really broad window which measured continuum. So this shows some sort of spatial extent as well. And then a plot of UV coverage to finish everything off. And now we're on to making images. So if we go to 19, well, at 19 in this particular example, but HIF make images. This actually shows images of the calibration sources. And at this point, the couple of things to check is just look at the images, make sure that they look like point sources, make sure that you don't see any severe artifacts in the data. This is the amplitude calibrator, so it's very bright and looks point-like. And then this is, the second set might actually be the phase calibrator. And I think it's the phase calibrator because I wasn't paying attention to the field name. Yeah, it is the phase calibrator. This is the phase calibrator. And the only way I can tell it's the phase calibrator is the fact that you can actually just barely begin to see the noise in the background. The fact that I have severe problems seeing the background noise means that the data were calibrated very well by the pipeline, which is good. So it tells us that we don't need to do anything to alter the pipeline calibration. Another thing to check here as well is, or actually a few other things, you see a series of stats here as well. We see the beam size. This gives us an idea of what the resolution could be. There will be another task where we'll see more details on beam size in a moment. So we're going to get something of 1.5 by 1 arc second for a resolution. So where is it here? So this gives the flux density for assuming the source is a point source, which is the case. You can see these basically came out okay. Okay, I'm not going to scroll through that much longer. So now we go to this Kifa image pre-check, and this is where we had the warning where we had an elliptical beam. This would actually be the type of thing where in QA2 it may require a little bit of discussion about whether this is an issue for using the science for or using the data for science analysis. If we page down here, we see various robust factors and various synthesized beam sizes that are expected for the data. And this is actually kind of a handy reference if you want to re-image the data. So it's like this tells you what you could expect for the beam size depending on how you set your robust factor. So if you're interested in higher resolution observations, you would try a smaller robust factor. If you're more interested in large scale or recovering as much large scale emission as you can, you would try a robust factor of 2. ALMA tends to default to 0.5 for a lot of data that's delivered to the archive because it's sort of a happy middle ground between those two extremes. And so this tells us that we can expect a beam about 1.3 by 0.9. But as the warning indicated, that is an elliptical beam, and that's going to be something that we have to keep in mind when working with the rest of the data. Next module that's worth looking at is this find Cont module, which is now actually working with imaging the science target data itself. And this is where the module tries to identify the channels which primarily cover continuum so that it can create continuum images of each of all of the data in each spectral window. And I believe it's the magenta bar, or excuse me, the cyan bars, which are identified as the continuum in this particular case. This may not necessarily be perfect because you can see it's working on a bi-channel basis. And so it may be the case that you can actually get detections of spectral lines if you try bending these data up more. In some cases, like this spectral window, the task doesn't think it's found any spectral lines at all. Just to show that one spectral window with a really bright spectral lines, like you can see, yeah, it's not going to put continuum identification there. And then finally, we have 3 more make images, or 4 actually. We have multiple more make image steps. Okay, so this first one is, which is 31, this example is a per spectral window continuum image. So this is taking those continuum channels and creating continuum images of each of them. This is nice as a preview of the images. It also gives us an idea of the quality of the calibration. So in these images, we don't see any severe striping in the data or any, we also don't see any like severe point source artifacts, which indicate that we may want to re-image the data using self-calibration, for example. Although that's always an option if you want to do that. But we don't see any severe striping artifacts in this, which means that the data were calibrated well. The next, and you can also scroll down and read through all of these scores and other information. The next one's an aggregate continuum image. Okay, this describes itself as an aggregate continuum image. Sometimes it's an aggregate flux image, I believe, which may include, and again, you know, it's like with these continuum images, there may be low flux spectral lines which are counted as part of the continuum. You'd have to look at the data in more detail to identify the presence of those lines. so this is an aggregate continuum image, looks relatively nice. We see there's this negative feature here, which may go away if we do a little bit of manual cleaning or something. Or this could also be, well, we can check the UV coverage. You could get negative features which are related to resolved out large scale emission, but this is a relatively compact configuration, so I don't think that should be happening here. So this is probably just related to the fact that the cleaning done by the pipeline is not perfect. But we get a nice structure here. We don't see that much striping or any other nasty artifacts. You can see there's only one image there. And then finally, this third one makes target cubes and then creates images of, okay, so this is peak line intensity, moment 8 images. You can see most of these are blank, but then if we skip to this one, this is the one with a really, really strong spectral line. And yeah, this gives us an idea of what the peak flux looks like for that spectral line. We also have something which looks like it could be a spectral line in one of the other spectral windows. Okay, and then that doesn't do anything else. Okay, and that is the whole of the weblog.